161. I hope you're okay after the storm. No one got washed out to sea or anything. So I wanted to hit some topics in chapter 1 that we didn't really have time for last week, and maybe we can go into a little bit more depth as well. Chapter 1 deals with matter, measurement, and problem solving. So we'll probably break up chapter 1 into a few videos. You can see the breakdown of the chapter right here. So first, let's talk about, atoms and molecules. It's just a basic introduction to the tiny particles of matter. Okay, so this is Tro's textbook, the 4th edition that we're looking at. Now, let me jump over here to the documents. The main idea in section 1.1 and also the introduction is that all of the material that you see around you, all of the material around us, it's called matter, is made of tiny particles. Okay, we cannot see these particles, but they're there, and we call them atoms and molecules. And I included ions as well. We'll get to ions a little bit later in chapter 2 or 3. Okay, but everything's made of tiny particles. What atoms are submicroscopic particles, and they are the fundamental building blocks of matter. So they're the smallest stable particle of matter. There are particles that are smaller than atoms, but they're not really that stable and they don't hang around long enough. So atoms are the fundamental building blocks, what everything seems to be made of. Today we know of about 120 different types of atoms. 118 exactly. Rarely in nature will we see or detect an isolated atom. They're usually combined together as molecules. So molecules are what you have when 2 or more atoms are combined in a certain arrangement. For instance, a water molecule has 3 atoms in the molecule: an oxygen atom and 2 hydrogen atoms, and they're combined in a triangular arrangement. The oxygen is right here, and it's attached to the hydrogen over here and the hydrogen over there. And it's like a triangular shaped molecule. All water molecules look like that. They're not straight, they're triangular shaped. So a certain arrangement of the atoms in a molecule. Ions are an atom or molecule that has become charged. We'll later learn that there are positive ions and negative ions, and opposite charges attract, and that affects the behavior of ions. Here are several examples of different types of matter and the particles they are composed of. For instance, helium gas. Suppose we have a container filled with helium gas. The particles inside that container are actually individual atoms of helium. The symbol for helium is He, capital H, lowercase e. And since this is a gas, we say it's He, and in parentheses put the G for gas. Now these atoms are all flying around independently of one another. And in the gas phase, the atoms are very far apart from one another. There's a lot of space. It's kind of like a bunch of balls floating around in space, and every once in a while one ricochets into another one. So a couple of these atoms might collide together. Okay. Further, the atoms of helium, they all look the same, and they're all pretty spherical. We can't see the atoms, but there are ways to detect that it's spherical. Another example is gold medal, right here. Now, solid chunk of gold. The symbol for gold is Au, from the Latin aurum, and since it's a solid, we say it's Au, and in parentheses S. Here, if you were able to see the particles in the gold, you would see that the atoms of gold are very tightly packed together. So the individual particles of gold are single atoms, but they're very closely arranged. They're packed against one another, and they extend in all directions like a three-dimensional solid object. So the gold atoms go in all directions, and further, the particles are rigidly held together and do not move around. So they may be vibrating a little bit, but it's not like the atoms are sliding past one another. Okay, in a solid phase, the structure is held rigid, and that's because the particles are locked in position, although they are vibrating a little bit. Okay, gold atoms are also spherical. Another type of material is liquid water. Here, if you're able to see the particles of water, they would all be those triangular shaped molecules that we mentioned before. And these molecules are also packed very closely together. But this time, the particles, the molecules, are able to slide past one another. And that's what makes a liquid different than a solid. The particles may be packed together, but they're able to move around relative to one another. So the particles flow, and that's why liquids flow. Now, inside each of these particles, these triangular shaped molecules, you have that oxygen atom, the pink one, and it's connected to a hydrogen over here and a hydrogen over there, and it's kind of triangular. And these atoms are all connected together. Well, the hydrogens are not really connected to each other, but they're both connected to the oxygen. Okay? I believe the angle in a water molecule between these three atoms, that bond angle, is like 104.5 degrees about. Now, since the particle is composed of 2 hydrogens and 1 oxygen, the formula for water is H2O, and in parentheses L, because we're talking about liquid water here. If we were talking about a solid piece of ice, it would be H2O and in parentheses S. Or water vapor, it would be H2O and in parentheses G. Another type of material is a salt crystal. Now, there's lots of different salts out there, but we're talking about table salt, which is sodium chloride. So here, if you're looking at a chunk of salt, chunks of sodium chloride are kind of cubical. If you look at them under a microscope, they're kind of cubical. And so you can imagine this is like the corner of one of those cubes. And if you're able to see the particles, you would see that the sodiums and the chlorines are arranged in an alternating fashion. You have a sodium here, and then a chlorine, and then a sodium, and then a chlorine, and then a sodium, and then a chlorine. But these particles are actually charged. So this is a sodium ion. It's a positively charged sodium ion, and then next to it is a negatively charged chlorine ion. And then a positive ion, sodium, and then a negative chlorine, and then a positive sodium, and it keeps on going. And those opposite charges attracting each other is what holds this stuff together. Okay, so they're packed together very tightly, and they're not flowing past one another. It's rigid, and so that's a solid. So the formula is NaCl and in parentheses S. Na is the element symbol for sodium because that comes from the natrium. I believe that's a Latin name. Okay. Now, the other main idea in the introduction and in section 1.1 is that the behavior of all matter is really determined by the behavior of the tiny particles that it's composed of. And we'll be looking at this throughout the semester. Okay? If you want to know about the properties of matter, why don't you look at the properties of the tiny particles it's composed of? And that's really what we do in chemistry. A good definition of chemistry is it's the science that seeks to understand the behavior of matter by studying behavior of its particles, which are atoms and molecules and ions. In section 1.2, we'll check back at the text here. Section 1.2, the scientific approach to knowledge. Here it talks a little bit about the scientific method, so I wanted to elaborate on this. The scientific approach to knowledge has been used for hundreds of years. Now, way back a few thousand years ago, back before measurements and experiments were really incorporated in science, people just used to think about the world around them. So if you wanted to explain, why nature behaves the way it does, you wouldn't really do any experiments, you wouldn't record any, measurements. You might just do what Aristotle did and just sit back and observe, maybe write a lot of notes. Aristotle took a lot of notes and recorded all kinds of data, and he wrote lots of books, but he really just observed it as a third person and then thought about what makes logical sense. Well, the reason the world is like this is because it seems to make rational sense. So that's really philosophy. Now, fast forward about a couple thousand years until you get to the 13th century, the medieval times. Well, now mathematics is starting to be incorporated with science, and science really begins to take off. And today, it's inseparable. You cannot really study science because it's gotten so far, if you're not able to really do experiments and, incorporate at least a certain amount of mathematical language. So the scientific approach to knowledge is really based on observation and experiment. An experiment is a highly controlled procedure designed to generate observations. Okay, so if you see something happen in nature and you want to learn about it, well, then you do experiments so you can generate lots of observations. For instance, suppose you're looking at the leaves on a tree in the fall, and you see that they will typically turn yellow around the month of October, and then they will eventually fall off the tree down to the ground. And this happens all over. Maybe not so much here in Hawaii, but it does happen in a lot of places. Okay, that's the autumn. Okay, so those are your observations, and you would like to explain why that happens, see if you can figure it out. What does it do that? How does it do that? Why does it do that? So what's your explanation? Well, you could just think about, what makes logical sense. Well, the reason, the leaves fall is because of, X, Y, Z, whatever reason you can come up with. But what we'll do today is we'll actually do experiments, and we'll study this in a controlled setting. We'll watch lots of trees turning in the fall. We'll watch lots of leaves falling. We'll probably take some measurements. We'll count the number of leaves. We'll measure how fast they fall, what color they change into. We'll see if anything else is involved. And so we'll record lots of data. And then after recording that data, that'll help us come up with a good, model for what's going on. So, for instance, when you do the scientific approach to knowledge, it's generally in 4 steps. First, you start with an observation. The leaves are falling from the trees. And then you might have a question. How does that work? That's usually your question. How does this work? Well, typically the next step, step 3, is to formulate a hypothesis. A hypothesis is a tentative explanation of the observation. So what do you think's going on? And it should be testable. So if we're talking about our tree leaf example, I hypothesize that the reason the leaves are turning color and falling to the ground is because there are little squirrels that are going around all the trees, and they're chewing on the leaves. That's causing them to die and change color, and then eventually they fall to the ground. So that's my hypothesis. And that's a pretty decent hypothesis, and at least that it's testable. Okay, I can test that. I can check to see if squirrels are actually doing that, if that is the actual reason. A bad hypothesis would be something like, the reason the leaves are falling is because there is a little troll who is invisible, and this troll that you can never see goes around and, you know, cuts all the leaves. Okay, but you can't see him. Well, that's a bad hypothesis because we cannot test it. Okay? Grandma, you know, sees gnomes in the garden, but every time you turn around, they disappear. Right? So you can't check that. Anyway, you want a testable hypothesis. And then, so I hypothesize that it's because of squirrels. Okay, so I would do an experiment. I would probably watch a set of trees picked randomly and watch all their leaves and see if I see any squirrels. Okay, and I wouldn't see any squirrels, or at least not any squirrels that are chewing all the leaves off. Okay, so that would contradict my hypothesis. So that would have been an incorrect hypothesis. And then I would probably pick another hypothesis. Okay, after that, and I would do experiments to check my new hypothesis. And you see, you keep on repeating that set of steps. And once you have a good hypothesis that's experiment confirms, well, then you've explained you explained what happened. So let's reiterate. Scientific approach to knowledge is based on observation and experiment. You have an observation, and this tells you what happens. It's anything about the world that we detect using either our senses, or instrumentation. And you will then typically want to explain your observation, why it happens, by formulating a hypothesis, which is a tentative explanation. You haven't confirmed it yet. It's tentative, an explanation of the observation, and it should be easily testable by an experiment. And the results of the experiment may support it or prove it wrong. So here's another example of the scientific method that your textbook talks about, but maybe we'll explain it a little bit more thoroughly here. And this is Antoine Lavoisier. Antoine Lavoisier lived 1743 to 1794. He was an outstanding chemist, one of the fathers of chemistry. He discovered a few new elements, and he actually constructed the first modern list of elements. So what did he have, like 30 something? I can't remember. We'll check it out in chapter 2 more carefully. But he gave us the first list of elements. Now we have a much better list today. So here's the periodic table. This is my gold periodic table. And we have about 120 elements in our list, and further, they're kind of arranged into different types. We got the metals, then we got the non. We'll talk about the elements later on, but this is the man, Antoine Lavoisier, back in the 1700s, and he used to do experiments where he burned stuff, and he would observe what happened in his combustion experiments. And he observed that substances increase in weight as they are burned. So he would work with sulfur, and phosphorus, and for instance, if he had a little bit of phosphorus, which is a white powder, lots of things are white powders, but so you start with some white powder, he would burn it, and then the ash that he has at the end, it would weigh more than what it started as. Okay, so it's kind of interesting. Now, that's his question, like, where did the extra mass come from? He explained these observations by hypothesizing, this is his explanation, that when a substance burns, it combines with a component of air. Okay, where does the extra mass come from? Well, it must come from the air. And further, the experiments that he performed supported this hypothesis. So you can imagine him doing the experiment like this, or this is how it happened. First, suppose he tried burning 10 grams of white phosphorus, okay, a little chunk of white phosphorus. Okay, you start with 10 grams, you burn it, and then you have 22.9 grams of white solid ash product afterwards. So this is your burned phosphorus. Okay, and his question is, how does the phosphorus increase its mass? And he hypothesized the extra mass comes from the air. So this is a pretty good hypothesis. It had to come from somewhere. Why not the air? It probably didn't seep up through the floor of the container. It probably came from the air. So the way he tested this hypothesis is he burned some phosphorus with air and also without air, and he compared the two methods. So without the air, he found that the phosphorus wouldn't even burn, like in an evacuated container. If there is no air, if you suck the air out and you put your phosphorus in there and you try to burn it, it won't even burn. So that is in support that the air is needed. Okay, but if you go back here, when he burned 10 grams of phosphorus and you end up with 22.9, that's an extra 12.9 grams. Okay, so let's get a little bit more quantitative. We just, he just figured out that air is necessary, but let's see if we can figure out that air supplies that exact amount of mass. So he does the experiment in a controlled environment. This is his procedures. He takes 10 grams of phosphorus, again, weighs this out. He has a sealed container containing 100 grams of air. Okay, you put the phosphorus into the container without letting anything else in or anything else out, and you burn it, and then you remove only the ash. And afterwards, he has his 22.9 grams of product, and then what's left inside is only 87.1 grams of air. I think I made a typo. That should... No, that's right. 87.1 grams of air. So you see, he increased, or the phosphorus increased by 12.9 grams, but the air inside decreased by that same amount. So the mass increased by the phosphorus is exactly equal to the mass lost by the air. So that's pretty good evidence that his hypothesis comes from, that is correct. The mass comes from air, because the numbers match up. You gain 12.9 grams here and you lost 12.9 grams there. They must be the same 12.9 grams. It must come from the air. Check. Hypothesis confirmed. And that's a pretty good application of the scientific method. Observation, okay, that gives you a question. You explain what you think happens, and then you test that. Now, if the hypothesis is wrong, then you'd have to come up with a new hypothesis and then run a new series of experiments to check it. Okay, so we can gain lots of knowledge about the world around us by doing this over and over and over again. Okay, we learn lots of explanations about the world around us. Now, what about um, laws and theories? Well, let's say a few things about them. Suppose you have similar observations that you make over and over again. Okay, so you observe similar phenomenon again and again and again. Well, they may be summarized into what's called a law. So, for instance, Antoine Lavoisier did one experiment, where 12.9 grams gained by the phosphorus is the same as the 12.9 grams lost by the air. But suppose he burned lots of things. Suppose he did like hundreds of experiments, and not just burning phosphorus, but burning all kinds of other substances. Well, and suppose that he always saw that the mass increased by what's being burned is the mass that's lost by the air. Well, then that's a pretty general type of observation. And further, suppose another scientist were studying some other type of chemical reaction, not necessarily burning, where one component increased its mass and then something else had to decrease in mass. So in other words, anytime a scientist studies some sort of chemical reaction in the laboratory, and anytime they see a certain mass increasing, they would always be able to observe somewhere else that same amount of mass decreasing. Well, now we can put all of these similar types of observations together in a law. And Lavoisier helped us do this, and he came up with the law of conservation of mass. And it says, in a chemical reaction, matter, or mass, is neither created nor destroyed. In other words, you never get mass out of it. It never just appears or disappears. It only moves around. Okay? If you lose it over here, you must gain it over there. And if you gain it over here, you must lose it over there. Okay? So that's the law of conservation of mass. All right, pretty important statement. Now, what's going on? Why do we have all of these laws? Is there a way to explain why the law of conservation of mass must always hold, in every single case? Now, in the last experiment, the extra mass must come from the air. Okay, but we're not always talking about burning stuff in air. Is there some other explanation that kind of covers all of these statements that are summarized, all of these observations that are summarized in a law? Is there something that can explain this law? Okay, kind of like a hypothesis explains an observation. What can explain this big law? Well, that's called a theory. Now, when you have a hypothesis that undergoes further testing and experimental checking of deductions that may be made from it, if it continues to agree with the results of experiment, the hypothesis is then called a theory. Okay? A scientific theory. So what this is just saying is that you saw in the last experiment that the 12.9 grams gained by the phosphorus is lost somewhere else. Okay? So suppose that's always the case. Anytime you see an increase in mass, you see an exact decrease in mass somewhere else. Well, that would help you predict what would happen in other experiments that you haven't even performed. Okay? It would help guide your work. You know that, if, you could predict what would happen if you burned 20 grams of phosphorus. Well, you should, increase in mass 12.9 times 2, right? Because now you're burning twice as much phosphorus. Anyway, so you would be able to use your previous explanation to help figure out what should happen in this new experiment that you haven't even performed yet. So a scientific theory, in your textbook, it's defined as a model for the way nature is, and it tries to explain not merely what nature does, but why. That's an important point. So a theory tries to explain why. Just like a hypothesis tries to explain why you saw an observation, a theory tries to explain why we have all these laws. For an example, closely related to what we were just talking about with burning stuff. The atomic theory proposed by John Dalton, this is about 100 years later, who lived from 1766 to 1844, almost 100 years later. He came up with the first atomic theory. He said, okay, I know what atoms are, and I'll tell you about them. The atomic theory proposed by Dalton explained the law of conservation of mass. Remember, the law of conservation of mass says you never lose mass and you never gain it. It's not created nor destroyed. It's always there. Well, the atomic theory tells us why. It proposed that matter is composed of tiny indestructible particles called atoms. Okay? Now, these atoms, he doesn't say where they came from. He says everything, all matter is made of atoms, and these atoms are indestructible. Okay? So they're not created and they're not destroyed. They're always there. When you have chemical reactions, the atoms simply, can be rearranged, but they're never created nor destroyed. So that does, in fact, explain the law of conservation of mass. The reason no mass is created nor destroyed is because mass is made of atoms, and if atoms are never created nor destroyed, then mass is never created nor destroyed. Okay? Since these particles are merely rearranged during chemical reactions and not created or destroyed, the total amount of mass remains the same. Okay, let's go back to our experiment. Now, before the experiment, we had 10 grams of phosphorus and 100 grams of air. You burn it. After the experiment, you had 22.9 grams of product and 87.1 grams of air. Okay? Now, what you should picture in your mind, the theory is telling us the way, this happens, the reason we didn't lose any mass, we had 110 grams total before, and we have 110 grams total afterwards. It's just that the mass was transferred from here over to there as atoms. And you can imagine, some of the air atoms moving in this direction. They're combining with the phosphorus atoms, right? So the atoms are rearranged. So in summary, observations and laws state what happens, and hypotheses and theories explain why it happens. All right? So I hope that helps. Next one is classification of matter. I think I'll stop the video and put this into another video.